All right, so our next talk is by Emilio Enriquez, and he's not a professor as yet. He is a PhD student, and he's doing his thesis on analysis of breakthrough listen data, and he might be the first one who will find a signal there. So welcome.
Thank you. Okay, can everyone hear me? Good, all right, great. So I'm happy to be here. Thanks for inviting me. Let's see, okay, this is my talk right here. I'll start by saying my disclaimer that I have some speculation fun slides, so bear with me. All right, so I want to tell you about the search for extraterrestrial intelligence in the context of this session, which is about the possibilities of having non-terrestrial life in the universe. So for that, I want to use two questions to help me guide you through my slides. So the first question that I have here is considering the possibilities of non-terran life, what types of signals from extraterrestrial intelligence could we detect? We have been talking about, well, what kinds of different types of life there could be. I'm a radio astronomer, so I have done my own literature search on this. And, well, I have some examples here. One that I didn't know about that was very interesting was the Horta, the weird-looking thing there, which is actually a silicon-based intelligent being. I have made my own classification. We have the good, the bad, and the ugly, of course. Oh. OK, so I'm telling you today about the search for extraterrestrial intelligence, right? Which actually is, we should say, the search for extraterrestrial technology. So it's not enough to be intelligent. You should be able to create basically technology that is able to be detected across very large distances across stars. We have a very good example, and that's the human technology. Right here, for instance, I'm showing ways that we communicate along large distances. So we have a high-power TV or radio station. We also have radars that are very strong. For instance, there is a geoplanetary radar, which is used to image asteroids, which is what you're seeing there. We can also communicate with lasers, very strong lasers, that also, as is shown over there. One thing that all of this has in common is that all of that are electromagnetic waves. So basically, our idea is that electromagnetic waves is the venue for communication along interstellar distances. And this is not a new idea. It has been around for a long time, since the 60s. And what I'm going to tell you now is why we think this is the logical way of communication, just giving some examples here. So light, either radio or optical or infrared, is relatively easy to generate. You require very low energy. It travels the fastest speed possible, which is the speed of light. We are also able to manipulate this into artificial forms. So one way is right here. This is one of my favorite examples, the Voyager spacecraft, which is now outside of the solar system. And this is what you see here is a dynamic spectrum, what we call. So we have frequency versus time. And what you see in the middle is that signal that is coming from Voyager. And something peculiar about it is this very narrow band. So it is only a few hertz in width. If you compare that to any natural source, astrophysical source, the most narrow that we can find are masers, which could be hundreds or thousands of hertz wide. So that already tells you, like, if you find something like this, it will be artificial. There are other examples. Well, one other thing about Voyager, just to kind of iterate on the first 2 points, is that the power required for Voyager to communicate with us is about 40 watts, which is the light bulb in your fridge. So you can really see right there how efficient a communication with electromagnetic waves is. So there is another way of using electromagnetic waves. Instead of having all your energy narrow into very narrow frequency channels, what you can do is have it in very short time, so a pulse. This is something that, for instance, infrared or optical SETI is also looking into. If you have lasers that are sending pulses this way. Another reason why electromagnetic waves it's, we think that the way to go, is that it goes through interstellar medium. So if you have a transmitter on the other side of the galaxy, and it's emitting in radio waves or in infrared, it will be able to go through dust and all the gas that we have in our galaxy. So at this point, there is no really need to invoke for any unknown physics or any unknown level of technology. Something that it has been known for a while now is that our own technology is already capable of sending signals through the whole galaxy. And I guess the last point here is that sometimes people say, well, we need faster than a speed light communication or something like this. But at the end, when we're talking about the creation of planets, we don't invoke physics that we don't know, right? So we use gravity to explain how the creation of planets works. In the same way, when we're talking about our own technology, we don't need to use unknown physics or unknown physics. So why then, when we're talking about extraterrestrial intelligence, should we invoke these things? So I don't think it makes sense. All right. One thing kind of in the context of this session, if we're thinking about non-terrestrial life, something to be looking at is the atmosphere of the planet. So what I'm showing here is basically a graph where you have wavelength here, and if you focus on the top one, it's telling you the absorption of our own atmosphere. And this absorption is related to the whatever elements that atmosphere is. If you have a different type of life that is not our own, maybe that composition is very different. And then where our atmosphere is absorbing, maybe for them it's not, and they might be transmitting at those frequencies. It's something to keep in mind, that we might not just look where we can, but hopefully at some point, for instance, we want to go to space and really look at other wavelengths and frequencies that we cannot from our own planet. Okay, so hopefully I'm trying to answer the first question here. So what types of signals, extraterrestrial intelligence, we can detect? So I think that would be electromagnetic, radiation, and we just need to, there is no specific frequency or wavelength that it would be preferred. We need to really look at all of them. Okay, so where should we look? How should we look for ET? I guess there are two, from the talks that we have here, I guess there are two examples. Either it's a biological life or non-biological life. If it is biological life, we think that it will be evolved on the surface of a planet. Whatever habitable zone would that be for whatever biochemical based life we're talking about. And likely it will evolve in that planet and will have the civilization in that planet. So you have these planets orbiting close by a star. In the case of machines, we can also try to make that argument. Maybe they still need to gain energy from the stars. They live as an energy resource. They would like to be living very close to a star. They might not necessarily be on a surface of a planet, but maybe still close to a star. So for these kinds of civilizations, the types of searches that we're doing now in SETI are concentrated in what we call targeted searches. So this is an example. This is what we have done last year, where we used the Green Band telescope, which is over there. It's the largest steerable telescope in the world. It's 100 meters in diameter. So it's very nice. It's very sensitive. But it's also only able to look at one pixel in the sky. It's very small location in the sky. So if you're looking only around a star, that's nice. That's what you want to do. So in this case, without going into much detail, at that point was one of the largest SETI searches ever done. So we did about 700 stars in the northern hemisphere. We didn't find anything, by the way. So there is another way, another possibility, and that's that life, either biological or not, decides that stars are boring, or you want to live in between stars or somewhere else. These are from my literature search, some examples. So if it is machine-based, we have the Borg that, from Star Trek, they're kind of half machine that like to live in between stars, I guess. And this kind of have come in the news lately from the Oumuamua asteroid. So this is Rama. It's also basically a very large spaceship where you can have basically a full biosphere inside it from R2 circular. So what I'm saying is, like, it doesn't matter what the origin of the life is. You can think of options of why they would not like to live close to a star. If that's the case, what we need to do are surveys. So this is one example of that. Here we're using the Parkes telescope with the right orientation, as Danny says. Danny Price, which one of our collaborators. Here we have the Milky Way, the plane of the Milky Way. So what we're trying to do with this telescope is conduct a survey of the full galactic plane. So we started that this year, and we're very excited about it. So in this case, then, we will not be only concentrated on the stars, but all the space in between as well. You can decide that, well, I want to do this quicker and not take a lot of time, a lot of months to conduct a survey. I want to look at a full galaxy in one observation. So this is one example of that. So this is from Robert Gray and Kunan Muli. They published this paper last year, and where they look at, with the VLA, they look at two nearby galaxies. So you have M31, the Andromeda Galaxy, and M33. So the circles that you see there are basically a beam, and one single observation that they took. So in one single observation, you're able to look at billions of stars and all the space in between them as well. So this is great, and we can talk about what kind of civilizations we'll be able to detect and so on, but without going into details, you can basically create, given the relatively long distances between galaxies, will take millions of years for that signal to arrive to us. Still, the power needed, it is not that large. If they have a beam signal pointing in our galaxy, it is still relatively low. And I'm saying low without numbers, but we can talk about strong numbers later if you really want to. OK, so there are other examples of types of galaxies that you can look at. So this is one of our collaborators, Brian Lackey. In this case, what you can do as well is look at very strong, very extreme environments, not like we have here in the Milky Way. So M82 is one of those. This is the closest starburst galaxy to Earth. And in order to look at the most, the region of the frequency spectrum where you will expect to be able to be more sensitive to these kinds of galaxies, is a much higher frequencies that we have done. So we are actually very excited about this project. Another example is that you can do surveys of galaxies. So in this case, we're conducting a relatively small survey of around 20 galaxies with both Parkes and Green Bank. We're almost done with the observations. In a couple months, we hope to do the analysis of this. Moving from radio to optical, you have Veritas. So this is a Cherenkov telescope, which is basically used for looking at the interaction between very high energy gamma rays, or also particles that hit the atmosphere and create some kind of shower of radiation. So they, in this case, they have 4 12-meter optical telescopes, and their field of view is 3.5 degrees. So that will allow you to really observe galaxies if you want to. If that's not enough, if looking at galaxies is not enough for you, if you really want to look in between galaxies, you want to do wider field SETI. There are options here too. With new technology that has been become available in the last few years, for instance, which are phase array telescopes. In this case, you don't have a dish, but you have thousands of dipoles spread around some land, and you can actually, with computers, phase them in a specific direction. So this has been done first at low frequencies, hundreds of megahertz, because that computationally that's easier. But these have hundreds of degrees, square degrees of field of view, which it really gives you a much better, well, a much larger piece of sky. In the future, once we have more computational power, you can move these to higher frequencies. So one example of this is Mantis. where you'll be able to do it at gigahertz frequencies. And you will have 200 degrees field of view. In the optical, it's one of the very cool projects that I'm very excited about. It's called the SETI project. In this case, collaborators in San Diego, Chile Wrights, for instance, they are creating what it will be a dome of Fresnel lenses. So with 126 Fresnel lenses, you will be able to see 10,000 square degrees. So basically, the whole sky at optical and infrared. You can even do more if you want, and this is a project from Emilio Enriquez in SETI Institute, where you have standard cameras pointing basically all around the sky, and you can distribute them around the whole world because they're very cheap. So, well, very cheap. And in this way, you will be able to see the night sky continuously. So you will have all the night sky all the time. So I hope with this we can answer the second question of where to look. So independent of the type of the origin of life, we think that either targeted observations make sense, but also all field sky makes sense. And I think in one of them we're doing already a lot of progress, and the other one, which is all sky observations, is all the SETI projects that are coming up. To finish up, there is a quote that I like to read that I learned about it not that long ago, that it has really inspired me. To understand the universe, you must know about atoms, about the forces that bind them, the contours of space and time, the birth of death of stars, the dance of galaxies, the secrets of black holes. But that is not enough. These ideas cannot explain everything. They can explain the light of the stars, but they cannot explain the light that shine the planet Earth. To understand these lights, you must know about life, about minds. With that, I want to conclude. Thanks. All right.